All right, we have got a much nicer day, I think, for you today. So we are still talking about accumulation functions. And in the last lesson, we talked about this definite integral. Okay, when we had that crazy lesson with the big summation. So again, the integral represents the area under the curve between A and B on that interval A to B. And this is the definite area, the exact area under the curve. And this integral, like the summation, represents like an S for the sum. You're taking all the pieces under there and you're adding them all together. Okay, and as of now, we've done it with Riemann sums. We've put rectangles and trapezoids under there. But this is what we're doing. We are looking for the exact area under the curve. So let us say that we know the interval starts at A, but we don't know where it stops. Okay, that would give us the interval A to X, where A is a constant and X is some unknown variable. So I want you to think about what we're saying. We have some function. We're going to start counting our area at A, but we don't know where it stops. Does it stop here, 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 here? We don't know. Okay, we're not sure where it stops. Okay, and that integral would look like this. So notice I'm using big F of X. It would be from the integral from A to X, starting at A, not sure where it's stopping. But now I'd have to put somebody other than X in here, so I'm going to call it F of t dt. I can't use X because I've named this function F of X. I've got to pick a different variable. All right, so let's look at example 1. And again, I just want to stress these have to be different variables. So let's say big F of X equals the integral from 0 to X of little f of t dt. Okay, so this is an accumulation function. It's going to start at 0 and it's going to gobble up area. Okay, like a little Pac-Man. Use the graph of f in the figure. So let's go ahead and label this the graph of f to find the values in the table from 0 to 5. Complete the table. Okay, so I'm going to function big F right here, and I'm plugging in 0. So I would get big F of 0, I'm going to write it out once, would equal the integral from 0, and I'm substituting in 0, of f of t dt. Okay, so think about what that means. You're starting at 0, and you're going to 0. So you're starting here, your little Pac-Man, you're going to eat up area, but you're stopping at 0. You're not moving. You have accumulated 0 area. 0 accumulation has occurred. Okay, so now I want to find big F of 1, so I'll write it out one more time. So big F of 1 would be the integral from 0 to 1 of f of t dt. So now that's saying start at 0 and accumulate all the area up until 1. Okay, now these are just 1 by 1 squares, so I can say that as an area of 1, 1 and a half. So I'm going to say, I'm sorry, that's 2.5. 1 plus 1 plus a half. Okay, and then we're going to keep going. Now we want the area from 0 to 2. So we're going to accumulate f of 2 from 0 to 2. So I'm starting at 0, and I'm going to add up all the area now up until 2. So I'm accumulating, like picture that Pac-Man, it's just going to eat up area as it goes. So again, I think I could just count these. 1, 2, 3, and those 2 halves make a 4. Then I'm going to eat up the area to 3. And that's just going to get me 5. I'm going to eat up some more area. It's another half, so that's a 5.5. And then I'm going to go to 5. Now, oh, be careful. This area is under the x-axis. So remember, we're taking that away. This is positive area we're accumulating. Now we're going to take this away. And again, it's a change. We're taking the change away. So I'm going to make that a 5. I'm going to lose that 5. So what we call this is an accumulation function. Now, if I wanted to graph out what this f of t function looked like, I could plot these points. At 0, it's at 0. At 1, it's at 2.5. At 2, it's at 4. At 3, it's at 5. 4, it's at 5.5, so someplace up here. And at 6, it's back at 5. And again, this is what big F would look like. And I can't actually connect them, remember, because I only know a few points. I don't know if this thing goes like this. I know your gut wants to do this, but we don't know that that's actually what it looks like. So all I can do is plot those points of F. Okay, so this accumulation function, it could be positive, it could be negative if we had more area under the curve. And again, it's just eating up area as it goes. So that leads us to the next very exciting thing tonight, which is the fundamental theorem of calculus. All right, now we're going to call this part 2. Now you might be asking yourself, well, where the heck was part 1? And most textbooks will go part 1, then part 2. Pretty much every textbook I've read. But the AP curriculum encourages us to do part 2 first, and then part 1. So that's what I'm doing here. We're going to do part 2, and then next week when we come back, we'll tackle part 1 eventually. So what part 2 says, and we are going to put this on a flashcard. So if you are on break at the senior trip here, we are going to put this on a flashcard when you get back. Don't let me forget. We are going to notice what we're doing. We are taking the derivative of an integral. How crazy is that? So we had a whole unit. The first half of the year was on derivatives. The second half is all on integrals, the area under the curve. And right now we're going to combine those. We are going to take the derivative of an integral. So what this turns out to equal is just f of x. So what's really happening is the derivative and the integral are almost canceling each other out. And we're still getting little f, but we're getting this x value inside of it. Okay? And the reason that's happening is derivatives and integrals are inverses of each other. Okay? They cancel each other out, just like multiplication and division are inverses. All right? So in example 1, the graph of f is the derivative of f. So f is considered the antiderivative of little f. So let me say that again. The graph of little f is the derivative of big F. So big F is the antiderivative of little f. Okay, so that might have sounded a little bit confusing. I get it. But at the end of this Unit 6 chapter, I think you're going to really understand these. It's not as bad as perhaps that sentence sounded. So let's work on just something simple here. I'm going to flip the page and look at example 1. We have big F of x is the integral from 2 to x. So this is an accumulation function. It's just eating up area. We don't know when it's stopping. And we want the derivative of big F. Okay, so if I take the derivative of big F, then I have to take the derivative of this integral. Right? Whatever I do to one side, I have to do to the other side, so to speak. Okay, so the derivative of big F just becomes big F prime of x, and the derivative and the integral undo each other, so I really just get this, but in terms of x. So I'm going to get 3x squared plus 4x. Easy enough? So let me just clear one thing up if you have a question. This 2, did this matter at all? Let me go back to the rule here. The rule said a is a constant. This number can be any constant. It could be negative 10, 55, pi, doesn't matter. If this is a constant and this is x, the derivative and the integral will cancel and this will just get substituted in. Okay, so that 2, what I'm trying to say, did not matter at all. All right, now, if you're thinking that was easy, it was. They get a little more complicated most of the time, which again, still isn't bad. But let's go on to a variation of the fundamental theorem of calculus part 2. Now, a lot of times, there's going to be an expression up here that just isn't x. Okay, it could be an expression of anything. It could be the sine of x. It could be x squared plus 10. There's some expression up there. So here's the rule. If I take the derivative of an integral and there's something besides x, you have to use the chain rule. Okay, so you're going to do the same thing. You're going to plug in that upper bound, just like we did here. We replace that. So this is going to be f of g of x. But now I have to multiply, because it's the chain rule, the derivative of that value. So times g prime of x. Okay, so let me say it again. Because this is more than just a plain old x, I have to use the chain rule. So I'm going to substitute it in, just like we did up here. But then I have to multiply by the derivative of that upper bound. And again, a is going to be any constant. So let's tackle a few examples like that. Let's flip back the page here. Number 2. So I have big F equals pi over 2 to x cubed, and I am taking the derivative. So big F becomes big F prime of x. Okay. The rule says the derivative and integral cancel each other out, but this number is going to get substituted in. So I'm going to get the sine of x cubed But now I have to apply the chain rule and multiply by the derivative of that value, so times 3x squared. And now it's done. All right, you try the next one. Give 3 a whirl. Taking this derivative, we have our constant, our expression. Give me a sec. Okay, I'm just going to take that upper bound, plug her in. So I'm going to get h of 4x. Right, the derivative and integral are going to cancel each other out, but I have to use the upper bound times the derivative of the upper bound, so times 4. Okay, now they could go one step uglier, and I'll show you that in a minute. I'm just going to go back here again. I know I said wrote chain rule here. I'm just going to make a note. You're going to plug in the upper bound, and then multiply by the derivative of the upper bound. So I'm plugging in the upper bound times the derivative of the upper bound. That is the chain rule part. Now, what if there's expressions in both the lower bound and the upper bound? Well, it's simple. You just apply the rule to both. Okay, so I'm going to put apply rule to both bounds. So we'll start with the upper bound. So I'm going to again, the derivative and integral cancel. So I'm going to get f of g of x. But that was more than just x, so I have to multiply by its derivative, g prime of x. Now we're going to subtract the lower bound version. So I'm going to get f of h of x times chain rule, its derivative, h prime of x. Okay, so I'm applying the rule of the upper bound just like we did, f of g of x times g prime with the chain rule. Then I'm going to subtract the derivative of the lower one, f of h of x times h prime of x. All right, let's try some examples. Let's try 4. So if I want to take this derivative of an integral, I'm going to get f prime of x. Okay, notice there's 2 variables, so I'm going to start at the top. So I'm going to get f of x times 1 minus, I'm going to get f times negative x. So I'm just going to clean that up. That's 5x. And that's going to turn into a plus 5x. So I'm going to get a 10x. All right, I just caught my mistake. So I plugged in the upper limit, 5 times x times the derivative, which is 1. Plugged in my lower limit, 5 times negative x, but times its derivative, sorry guys, times negative 1. So that actually is going to turn into a minus, and I'm going to get 0. And I apologize, I can't go back and edit that. So I'm going to say this one more time. So my f prime of x, I'm going to plug in the upper bound. So 5x times the derivative of the upper bound, minus, plug in the lower bound, 5 times negative x, times the derivative of the lower bound, negative 1. So that gets me 5x is negative and negative is positive times a negative, minus 5x is going to get me 0. Sorry about that. All right, I'm going to do better on the next one. All right, so I'm going to I've got variables in both, so I'm taking the derivative. So all I'm going to do is start with the upper bound and substitute that in. So 3x squared minus 3x times the derivative of the upper, so times 3. Minus, I'm going to substitute the lower in. So that's 2x squared minus 2x times the derivative of the lower times 2. So let's check my math here. This is going to be 9x squared minus 3x times 3. So 27x squared minus 9x. This is going to be 4x squared minus 2x times 2. So that's 8x squared minus 4x. And I'm going to subtract those quantities. So that's 27x squared minus 9x minus 8x squared plus 4x. What does that get me? 18x squared minus 5x. Okay. All right, so we're ready for some practice. So I'm going to pause it. I'm going to let you practice, and then I will show you my answers as I go through this. And I can talk anything out. But take a minute, try these. and then I'll turn it back on and give you my answers in a minute. All right, so again, I had x cubed, just plugged in the upper bound. Here there was no place to plug it in, so it was just 5. Here I plugged in the upper bound. Again, its derivative is 1, that's why I don't have to worry about anything else. Again, I just got cos x. Okay, so now plugging in the upper bound times its derivative. So this became x to the 6th times 2x, would be 2x to the 7th. Again, I'll let you kind of look at them, compare, see if there's pause it, see what you see. 7 perhaps, I plugged in the sine. The derivative of sine is cosine. So I am getting cosine over sine. So again, that wouldn't be a choice. We'd have to recognize that as cotangent. Again, I plugged in this. Those cancel. So 3x times 2x is 6x squared. I think the rest were pretty straightforward. Okay, but it's plug in the upper bound times the derivative of the upper bound. Oh, there's some more. Again, try these ones on the back. I'll put it back on and show you my answers. Okay, so again, 13 was nice. Plug in the upper bound times the derivative of the upper bound. 14, I had to do the double one. Plug in the upper bound times the derivative of the upper bound, minus plug in the lower bound times the derivative of the upper bound. After I cleaned up, I got 8. Same thing, plug in the upper bound times the derivative of the upper bound, minus plug in the upper bound times the derivative. And same thing here and here. So feel free to pause it and check out my work. All right, moving on, we've got some AP questions. These are just all types of questions you would see. So given g of x is the derivative of the integral, what is g of negative 4? Okay, so g of negative 4, I'm just substituting in negative 4 into g, is the derivative okay, so if I take this derivative, the derivative and the integral cancel, that substitutes in. So I've got x squared plus 9, and then I'm going to substitute in my negative 4. So negative 4 squared plus 9 is 16 plus 9. I get the square root of 25, so I think that's leading me to 5. 19. The graph of the function f on the closed interval 0 to 6 is shown above, so I labeled that f. H of x is this function. Okay, so we're going to start to deal with two functions at a time. Here's f, here's h of x. So I want h prime, so I'm going to go to function h. I'm going to take its derivative. This is the derivative of an integral, so I'm going to take that upper bound, substitute it in, times the derivative of the upper bound is 1. So now it wants h prime of 3, which is really just equivalent to f of 3. Happen to have a graph of f of 3 is equivalent to 0. Okay, so we're going to do a lot of graphs like this where we're given a function, given a different function, and we'll use them interchangeably here. All right, we've made it to the last one here, figure 20. So again, it's an AP type question. The figure above shows the region A, which is bounded by the x-axis, y-axis, and this graph. So we're talking about this region here. Obviously, it's shaded in a little bit. And the vertical line x equals b. Okay, so let's go ahead and write an integral that represents this area itself. So that area would be the integral from, I want to add up all the pieces between 0 and b, and that are sitting under the curve 1 minus cos x dx. Okay, so again, this is my width, this is my height. The height of the function, the width is dx. If b increases at a rate of pi over 2 units per second, how fast is the area of reaching? So the moment they said how fast, we're going to related rates. We want to take this derivative with respect to time. So I'm going to get dA dt equals, now remember, the derivative of an integral is simple, right? They cancel each other out. You plug in the upper bound times the derivative of the upper bound. So 1 minus the cosine of b over b times the derivative of the upper bound with respect to time would be dB dt. Okay, now it says if b increases at a rate of pi over 2, that would be dB dt. specifically when b is pi over 3. So I'm going to substitute in my pi over 3 for b times db dt, which they said is pi over 2. All right, cleaning up a little further, cosine, this is 60. Cosine of 60 is 1/2 over pi over 3 times pi over 2. 1 minus 1/2 is just 1/2 pi over 3 times pi over 2. And I'm just going to do a quick keep, change, flip. So I'm going to say that's 1/2 times 3 over pi times pi over 2. So I think my pi's are going to cancel, and bam, I'm going to get 3/4 for dA dt. All right, well that does it. See ya when we see ya.